Deja vu all over again. We're going to be talking about electrophilic addition once again, but this time we're going to be talking about alkynes, right? We've talked about electrophilic addition and alkenes, and one of the things you'll kind of notice about these alkyne systems is that a lot of the reactions that we learned for them really have like some direct application to our alkyne system here. If you kind of think back to what it meant to do an electrophilic addition, and I said that it's really almost like an XY or AB system, kind of adds as a hat, right, across a multiple bond. Well, it turns out that now we have the opportunity to do this 2 times because we've got 2 multiple bonds in there. And so in terms of like the progression of the organic course, right? Like usually the foundation is the alkenes, you build in a little bit of alkyne chemistry, and then we'll start to gradually make these systems a little bit more complex. One of the things you'll notice is that a lot of the mechanisms are the same, just with a couple of curveballs thrown in, like I've been saying in different lecture videos. So let's take a look at just in 2 different types of electrophilic additions that are going to be really important, especially for our synthetic protocols. Back in the alkene side of things, we saw this reagent before, right? H2 palladium on carbon, or quite honestly, H2 and any kind of fancy little catalyst there. And it turns out that the same thing that happened in the alkene case is going to happen here. But it turns out that now we've got 2 bonds to react with. So we are actually going to end up with adding H2 twice. And what we're going to form as a result is pretty simple, right? We are going to have, let's actually draw them out here. We're going to take whatever our terminal alkyne is, and by the way, it also works for an internal alkyne, is you simply keep adding protons until you end up with a single bond, right? And so this is once again called catalytic hydrogenation, or reduction of an alkyne to make an alkane. The problem is that when you look at this, many times it would be really, really useful to just stop at the alkene, right? And so the 2 kind of curveball reactions that I'll show you have to do with ways of doing that, but also controlling where my H's add, which is yet another kind of exciting thing about alkynes. So it turns out that if you want to stop at the halfway point, you have really 2 options. One is H2 with what's called Lindlar's catalyst. And Lindlar's catalyst has, you pretty much take a palladium on carbon system and poison it with some sort of like either barium sulfate, poison, or there's a bunch of different poisons, but let's just say that a Lindlar's catalyst has kind of a poison, right? And so in that particular way, you're going to be able to add H, and you're just going to add 1 set of H's, right? And so in a case like this for a terminal alkyne, so in this particular case, we end up with just a simple terminal alkene, right? And so it's very similar to that 1 equivalent idea, right? Where if we just want hydrogen to react once, well, we would like to just be able to say 1 equivalent of hydrogen, but unfortunately the reactivity of hydrogen is a little bit different. So what we have to do instead is to take a catalyst and poison it a little bit so that it doesn't go all the way. The problem is that, terminal alkenes are not that exciting. So let's take a look at a little bit more of an exciting system than just this like terminal alkyne right here. So let's start now with an internal alkyne, and we're going to take that Lindlar's catalyst, and I want you to notice the interesting thing, at least interesting to me. It turns out that we specifically get this product. And I'll highlight this in blue. You'll notice by the use of Lindlar's catalyst, we specifically get this cis type of alkene. that's really useful, right? Anytime you have really tight control over like the products that you form, that's going to be a really important thing in our organic chemistry. So if we would like to just add H2s in a syn fashion, this is a really, really good system to use. It turns out that anytime you can do something where both H's add on one side, wow, wouldn't it be cool if we could have one H add the top side and one H add to the bottom side? Turns out that's yet another good note card reaction, which we're not going to look at the mechanism for because it is so wacko. So these conditions right here, you're quite literally dissolving sodium metal, right? Solid sodium metal into ammonia solvent. Really exciting, really dangerous reaction to do. This is called dissolving metal reduction. But the important thing to recognize is that this witch's brew will end up with the exact opposite regiochemistry in your product. It turns out that those H's will actually add to opposite sides of that compound. So now you can notice that we've got two very interesting products when you consider the fact that we could add using some of those stereospecific reactions from the alkene side of chemistry, and we could actually end up with very specific stereochemical outcomes by using one of these two products, right? And so these two steps are going to be pretty important in a lot of our alkyne syntheses that we're going to be kind of highlighting again on Monday. So these are two really good note card reactions. Let's take a look at a couple of other important reactions. Well, if you remember our HBr addition and that idea of a double bond kind of swinging out and attacking a particular electrophile, same exact thing is going to happen here, but with the exception of the fact that now we have either the possibility with two equivalents of this thing, adding bromines twice. So with two equivalents, you're going to take this system and add two sets of bromine, or alternatively, we can add one equivalent of bromine, and then you'll end up with your alkene product, right? And so one of the things that's going to be a really important set of reactions in our synthesis lectures for next week is kind of a combination of the reactions that I just showed you involving reductions, and then these reactions involving brominations, and then the previous video lectures, reactions with the acetylide anion. All of that's going to kind of come together with the ability for us to make all kinds of different really cool products just with this one pretty simple functional group. So just like with HBr, we saw that, the fact that alkynes act very much like alkenes, just, taken two times. You can do a very similar thing with halogens, right? Just like we saw before, we could use either, well, let's do two equivalent right here. We could either use two equivalents of Cl2, in which case our product would be as chlorinated as possible. Or we could use one equivalent of Cl2 and end up with this kind of anti-addition product right here with an alkene. And so these two sets of reactions that we just talked about, both these chlorinations and then the brominations we talked about on the previous step, give rise to a really easy way of us to make alkynes. And so I'm going to show you that just so that we can eventually use that. And I think it's on your homework, but also in next week's video lectures. So I wasn't really sure where to put this reaction. It just kind of is a random reaction that sometimes is helpful. And that is how to make an alkyne from halogenated alkanes. So it turns out if you're able to get to the kind of the double halogenated alkane, by the way, it could have halogen groups on side-by-side carbons or also halogen groups on the same carbon. If you treat this thing with a really, really strong base like KOH, and heat the bejesus out of it, you're often able to get to an alkyne. So I'm pretty sure this makes an appearance on your homework somewhere. So that's it for this week. Make sure you eat a lot of turkey and have a good Thanksgiving, and I'll get back at you on Monday.